and then limit n goes to infinity. And then I'm going to bring in the natural log, n over n plus 1, and then to the n, right? But that n is going to drop out in front. That all right? Now, let's look at the indeterminate form we have. N goes to infinity. This piece is going to infinity. Times, we already know n over n plus 1 is going to 1. Natural log of 1 is approaching 0. So this looks like infinity times 0, right? That's still an indeterminate form. So when you see this, what do? Drop one of them down. And in this case, I think the n being dropped down is probably easier, right? So I'm going to go natural log y equals limit n goes to infinity. This is getting kind of ugly. Natural log of n over n plus 1 over 1 over n. Yeah? I have an idea.
Wouldn't it be easier the other way?
What?
Wouldn't it be easier the other way?
Easier to do what?
Maybe put the ln underneath.
Well, if you drop it down, it's going to have to be ln of all that to the negative 1. The whole thing, like, or 1 over the whole natural log. You can't just move the natural log down here. It would have to be 1 over the natural log. Make sense? And then if you take derivative of that, that's going to be kind of messy. Okay, so here's what I'm thinking. If we take the derivative of the top, I should be okay with that. Derivative of the bottom should be okay. I'm wondering, should I use the property of logs to split this into 2 logs? Like, can't we do division inside becomes subtraction? Maybe. Let's see how bad it is. Maybe we'll have to do that. Okay, but I'm gonna try not do it and see if we can survive without doing that. So I have natural log y equals, let's see, limit n goes to infinity. I'm using L'Hopital's rule right now. Derivative of the top. So what is a derivative of natural log of this fraction? 1 over that fraction, right? 1 over this fraction? And what's 1 over this fraction? It's just that fraction flipped. So isn't the derivative of the top n plus 1 over n so far, right? Times the derivative of what's in here. Don't forget chain rule, right? You have to take derivative of what's in here. And that's going to require quotient rule. Yeah? Yeah, okay, we'll do a quick quotient rule. Quotient rule on the inside of this, derivative of the top, 1 times the bottom, minus derivative of the bottom times the top, over bottom squared. Right? What is that? N minus n. I think we just get 1 over, right? N plus 1 squared. 1 over n plus 1 squared. Yes? All over derivative of the bottom. Negative 1 over n squared. Right? This is the same as n to the negative 1. Derivative of that is negative 1 over n squared. Are y'all okay? All right. I see a little bit of cleaning up we can do. I see that one of the factors of n plus 1 cancel. Right? One of them? All right, so I have natural log y equals limit as n goes to infinity. I have on the top 1 over n times n plus 1, right? Yes? And on the bottom, negative 1 over n squared, which I can flip as n squared over negative 1, can't I? One of the n's cancel? We're almost there. Natural log y equals the limit as n goes to infinity of n over n plus 1, right? But I have a negative there, right? So why don't I just throw the negative up top? All right, we're there. What's that limit? L'Hopital on that? Negative 1 over 1? Just get negative 1. So natural log y equals negative 1. Are we good? Now, we need to get back to y. So how do you undo the natural log? E. So you take e to the natural log y equals e to the negative 1. So y is equal to e to the negative 1. And wasn't y what we were trying to find? Like that was the limit we were trying to find. So remember, e to the negative 1 is the same as 1 over e. What's our conclusion? It converges, right? This is, I had stopped and done some scratch work, right? We had actually stopped at the point where we were looking at, we were at the limit, n goes to infinity, absolute value, we were at n over n plus 1 to the n, right? And I had stopped and came and did all this work. I figured out that that limit is 1 over e. So this is this right here is our L. That's less than 1, obviously, yes. E is about 2.718. So this series converges. That was a lot of work, but it was... The thing about the ratio test is that it's not like the comparison where you have to come up with something and you could pick something that's wrong and then be going kind of in circles trying to grab something out of the air. With the ratio test, if it works, then it's just a mechanical process of you applying a limit. That's all it is. Okay? All right, that was fun. Let's do another one.
Would that have still worked if you would have ended up splitting it up, like when you had first taken the natural log and you would have done
Like I was saying, could we use the subtraction on it?
this minus the...
Let's see, we would have had natural log n minus natural log n plus 1. I believe that's what we would have had, right? Over 1 over n. A quick derivative on top would have given me 1 over n minus derivative of this would have been 1 over n plus 1 over bottom negative 1 over n squared. Following me? Then I would have got a common denominator on top, so it would have been up n plus 1 minus n over n times n plus 1 over negative 1 over n squared. And then I would have been at 1 over n times n plus 1 over negative 1 over n squared, and then I would have flipped it and we would have been exactly where we were earlier. So in hindsight, this seems a little cleaner because that derivative of this was a lot cleaner than the derivative with the chain rule in there. I saw it, but I don't think that would have been something natural for everyone to do, so I wanted to go the other route. Yeah? Okay. That's a good thing about math. I like this part about math. You know, like you do it 2 different ways, you should get to the same result. Like there's no like, oh, well, if you do it that way, then you're going to get a different answer because, well, you did a different way. It should all work, right? Okay. All right, for the next one, this one's going to be a little weird. In fact, it's going to be very weird because you've never seen anything like this. Does this converge or diverge? Question. So I'm going to give you the series. Here it is. 2/5 plus 2 times 6 over 5 times 8 plus 2 times 6 times 10 over 5 times 8 times 11 plus 2 times 6 times 10 times 14 over 5 times 8 times 11 times 14 plus, I'll go one more, 2 times 6 times 10 times 14, any guesses? 18 over 5 times 8 times 11 times 14 times 17 plus dot, 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 dot. Yeah, so these are weird, right? They almost look like factorials, but they're not. Okay, these are not factorials, and the reason, obviously, is because they're missing a bunch of stuff, right? Like, even if you just look at this first one, 2 times 6, if that's a factorial, the best we would have hoped for is like 6 factorial. But that's 6 times 5 times 4 times 3 times 2 times 1. We only have the 6 and the 2, right? Forget the 1, it doesn't need to be there. So we're missing the 5, 4, and the 3. Here, we're missing 3, 4, 5, and we're missing 7, 8, 9, right? So it's not a factorial. Can you what?
Can you make factorial do something else?
there are ways to kind of manipulate factorials to kind of get this to happen, but I'm going to show you the technique that the book uses, and I think it's a little cleaner if we just approach it this way. All right. So let me ask you this. Just look at the numerators for right now. 2, 6, 10, 14. Just as a sequence, can you generate that sequence for me? Okay, what would you use as a formula to generate this sequence? So they all jump by how much? 4 each time. So that tells you automatically you're going to need a 4n in here. Now it's just a matter of can you now like tweak it to make it spit out a 2 first, and then a 6, and then a 10. So I heard 4n minus 2. So if I start at 1, I'm going to get 2. If I go to 2, I'm going to get 8 minus 2, that's 6. 3 is 12 minus 2 is 10. So this, do you agree, would generate this sequence?
Yeah.
The problem is this is not this over something. We haven't talked about the bottom. But do you see why this is not this? Because if I plug in 1, what do I get? I get 2 on top, right? Forget the bottom. We'll come back to it. But if I plug in 2, what do I get? Just the 6. I don't get the 2, right? If I plug in 3, I get the 10, but I don't get the 6 and the 2. So even though it's connected, this is connected to what's happening there, it's not what's exactly happening by itself. Understand?
Did you multiply by something that would kind of keep track of how many times it's done?
Yeah, I mean, there are ways we can mess with it, but let me show you the way, and you're just going to be like, okay, sure, all right. All right, we can do that. How about the bottom? How can you generate that bottom one for me? 5, 8, 11, and I'm going to get rid of this. So these are all jumping by how much? 3, so I need a 3n, and then what do I do to this to make it start at 5? Plus 2. Make sense? That will generate that 5, 8, 11. Okay, so here's how we deal with it. And I know this is going to look weird. Sum n equals 1 to infinity. What I'm going to do is I'm going to show you the pattern of what I want this to be in here. My formula in here needs to be 2 times 6 times 10 times ... and stop at, oh, I erased it, 4n minus 2. Just write that down. We'll talk about it in just a second. 5, 8, 11 times ... until you get to, not 5n, 3n plus 2. Okay. So what this formula is, and this is why I said you haven't seen anything like this yet, is what this formula does is it shows you the pattern of what's happening. And the n is going to dictate where you stop the pattern. So if I actually try and write this out, let's let n be 1 here. What I'm going to do, if n is 1, is I'm going to come out to here and plug it in. So what would I get if n is 1? I get 2. So what I'm supposed to do is start this pattern, but stop it at 2. So that means I only go and I only grab the first one. So this will be 2 over. And now n is 1, plug it in here. I'm going to stop at 5. And here's the pattern, 5, 8, 11. So I stop at 5. Done, right? Plus, now let n be 2. If n is 2, where am I going to stop? I'm going to stop at 6. So I start at 2, go 2, then 6. And then on the bottom, 5, and then 8. And then on the next one, n is 3, I'll stop at 10. I'll go 2, 6, 10. On the bottom, 5, 8, 11. That's how we deal with it, all right?
Is there a name for something like that, or is it just...
No. Now, there is a better way. I'll show you real briefly a better way. We know what this means, right? Sum, a sub n. This is a1 plus a2 plus a3 forever, or depending on what these limits are. This capital Greek sigma was a capital S, right? Capital S stood for sum. What if instead of me adding things together, I wanted to multiply things together? Like instead of plus, 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 I want times, times, times. We have a different symbol for it. It's a product. What's the Greek capital P? Capital Pi. So if you do capital Pi, n equals 1 to infinity of a sub n, this is a1 times a2 times a3. That's an infinite product as opposed to an infinite sum. Now, if we were allowed to use this notation, which we're not using this notation, if we were allowed to, then what we could do here, instead of that notation, is we could have done product n equals 1 to infinity, and then we could have used our formulas right away. 3n plus 2. You see, because this would have worked.
How come we can't use it?
Well, we would need this in that formula. I take that back. This would actually have to be embedded. It's a little tricky. You would have to embed this in, so that capital product would be up here and then down here. You'd have two capital products within the summation. It's kind of weird. That's why we don't do it. Okay? It's just a little too complicated. All right. So, does it converge or diverge? That's the question, right? So I'm going to run a ratio test. And it's going to seem weird for me to run a ratio test on this, but let's try it. I'm going to leave it right there, erase this, and here comes my ratio test. I'm going to take the limit as n goes to infinity, and I'm going to do a sub n plus 1 over a sub n. Give myself some room here. What is a sub n plus 1? So you're going to this formula, right? This is our formula. And I'm going to replace the n's with n plus 1s. So let's just see what would happen if I replace that n with n plus 1. What would this become if I replace the n with n plus 1? 4 times n plus 1 minus 2, which would be 4n plus 4 minus 2, which would be 4n plus 2. Agreed? And then this one, if I replace the n with n plus 1, 3 times n plus 1 plus 2, which is 3n plus 3 plus 2, which is 3n plus 5. Now that's the more complicated way of doing it. If you just think about it, what's happening each time I move out? I just keep, what, adding 4, add 4, add 4. So what would the one right after this one be? This plus 4. What's this plus 4? 4n plus 2. Okay, these are going up by 3, 3, 3. So what's the one right after this one? This plus 3. It's that, right? Okay, that's what's happening. So I'm going to put a sub n plus 1 on top, which is 2 times 6 times 10 times dot, 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 dot. And now leave a gap right here on purpose, and then put your last one, which would be the 4n plus 2. Understand that that's what happens if I go out to a sub n plus 1? Over 5 times 8 times 11 times dot, 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 times, leave a gap, and then this one is 3n plus 5. That's a sub n plus 1. Over just a sub n. So this one doesn't go out as far, does it? This one goes and it stops at 4n minus 2. And then this one right here stops at 3n plus 2, right? That looks pretty nasty.
It's really nice, actually.
But, yeah, you see I left a gap here for a reason. What goes here?
4n minus 2.
4n minus 2 goes here, and 3n plus 2 goes there. Those are the ones that are right before, aren't they? And you can start to see, I'm going to do a flipping here, but you can start to see that when I flip this one up and bring it like this, a bunch of stuff's going to cancel. Almost everything, right? Yep, except the last two. So, but I'll be thorough and I'll write it out.